What if I told you that right now, at this very moment, there are cosmic monsters spinning so fast that they're literally dragging the fabric of space, and time itself around them like water spiraling down a drain? And what if I told you that some of these black holes are rotating at 99.9%, the speed of light at their event horizons, so fast that if you could somehow stand near one, time itself would become meaningless, and space would twist into directions your brain can't even comprehend? Here's the thing that's going to absolutely blow your mind. We're not talking about some theoretical possibility buried in obscure physics papers. In 2013, astronomers measured a supermassive black hole called NGC 1365 that's spinning at about 84% the speed of light. That's roughly 150,000 miles per second at its surface. And it gets wilder. In 2019, researchers at NASA confirmed the existence of stellar black holes spinning even faster, approaching what we call the maximal spin limit. These aren't just fast-spinning objects. They're tearing reality apart. But here's what's really going to mess with your head. These black holes shouldn't be spinning this fast. According to our basic understanding of physics, there are limits. There are rules. And these cosmic behemoths are dancing right on the edge of those rules, threatening to break everything we think we know about the universe. The question isn't just, why do they spin so fast? The real question is, what happens when something spins so fast that it breaks the laws of physics? Before we dive into this mind-bending journey, do me a favor, hit that like button and subscribe, because over the next 4 hours, I'm going to completely change how you see the universe. And drop a comment telling me where you're watching from and what time it is there right now. I want to know if you're losing sleep over black holes like I am. Are you in Tokyo at 3 a.m.? London during your lunch break? New York in the middle of the night? Let me know, because we're all about to take this cosmic journey together. Now, let's start with something that seems simple, but is actually going to be our gateway into understanding one of the most extreme phenomena in the entire universe. Think about the last time you watched ice skaters on TV. You've seen it. They start spinning with their arms stretched out, and then they pull their arms in close to their body, and suddenly they're spinning so fast they become a blur. That's called conservation of angular momentum, and it's exactly the same principle that makes black holes spin faster than seems physically possible. But here's where things get interesting. Ice skaters have friction. They slow down. They stop. Black holes? They exist in the vacuum of space where there's essentially no friction. Once they start spinning, they just keep spinning and spinning and spinning for billions of years, forever. But that's just the beginning of this story. See, black holes don't just appear out of nowhere, already spinning at relativistic speeds. They have origin stories, and those stories are violent, chaotic, and absolutely fascinating. Let me take you back to 1916, just 1 year after Albert Einstein published his general theory of relativity. A German physicist named Karl Schwarzschild was serving on the Russian front during World War I, and while dodging bullets and artillery fire, he did something extraordinary. He found the first exact solution to Einstein's field equations. Think about that for a second. This man was in a war zone, and he was doing calculations that would fundamentally change our understanding of the universe. Schwarzschild's solution described what happens when you compress all the mass of an object into an infinitely small point. He discovered black holes, though he didn't call them that. He called them singularities. But here's what Schwarzschild didn't account for: rotation. His solution assumed a perfectly spherical, non-rotating black hole. And in the real universe, nothing is perfectly still. Everything rotates. The Earth rotates. The Sun rotates. Our galaxy rotates. So naturally, when stars collapse to form black holes, they're already rotating. And that's when things get really interesting. Fast forward to 1963. A New Zealand mathematician named Kerr was working at the University of Texas, And he solved one of the most difficult problems in theoretical physics. He found the solution to Einstein's equations for a rotating black hole. This wasn't just an incremental step forward, this was a revolution. Kerr showed that rotating black holes have completely different properties than the simple Schwarzschild black holes. They're not just spheres anymore. They're flattened at the poles and bulging at the equator like cosmic spinning tops. And they do something even more bizarre. They drag spacetime itself around with them. Imagine you're stirring honey with a spoon. The honey near the spoon moves fastest, and even the honey farther away starts to slowly swirl. Now imagine the spoon is a black hole, and the honey is spacetime itself, the actual fabric of reality. That's what Roy Kerr discovered. He called it frame dragging, but that term doesn't do it justice. We're talking about spacetime itself being twisted, warped, and dragged in circles around these spinning monsters. Now here's where we need to establish some foundation, because the next 3 hours are going to build on these concepts in ways that are going to progressively blow your mind. Let's talk about what angular momentum actually is, because understanding this is crucial to understanding why some black holes spin so insanely fast. Angular momentum is, in its simplest form, the momentum of rotation. Everything that spins has it. When you ride a bike, the wheels have angular momentum, and that's what keeps you stable. When a figure skater spins, they have angular momentum. When a star collapses into a black hole, all of that star's angular momentum has to go somewhere. And here's the key. Angular momentum is conserved. It can't be created or destroyed, only transferred. Think of it like this. Imagine you have a pizza dough, and you're spinning it to stretch it out. Now imagine you suddenly pull all that dough into a much smaller circle. What happens? It starts spinning faster, much faster. That's conservation of angular momentum in action. The same amount of rotational energy is now concentrated in a much smaller space, so the rotation speed increases dramatically. When a massive star, let's say 20 times the mass of our sun, runs out of fuel, its core collapses catastrophically. In less than a second, a sphere of matter roughly the size of Earth compresses down to a point just a few miles across. All of that star's rotation, all of its angular momentum, is suddenly concentrated in an incredibly tiny space. The result? The newly formed black hole spins. Fast, really fast. But here's the twist that's going to set up everything else we're going to talk about. Black holes don't just form from collapsing stars. They also form from collisions between existing black holes, or by consuming massive amounts of matter from their surroundings. And every time matter falls into a black hole, it adds its angular momentum to the black hole's spin. It's like a cosmic figure skater constantly catching objects thrown at them while spinning. Each catch makes them spin even faster. Now, before we go deeper, let me make sure you're still with me, because here's where we start introducing some mind-bending concepts. There's a number that's going to become really important in our story. It's called the spin parameter, and physicists represent it with the letter A. For a non-rotating black hole, A equals 0. For a maximally rotating black hole, one spinning as fast as physics allows A equals 1. Or, more precisely, A equals the mass of the black hole times the speed of light. In 1974, a physicist named Kip Thorne, who would later win the Nobel Prize and serve as a scientific consultant on the movie Interstellar, proposed something that would become known as the Thorne limit. He calculated that black holes in the real universe probably can't spin faster than about A equals 0.998. That's 99.8% of the theoretical maximum. Why? Because as a black hole spins faster and faster, it becomes increasingly difficult for it to capture more matter in a way that would make it spin even faster. The black hole's intense rotation creates forces that tend to fling matter away rather than letting it fall in neatly. But here's what's going to blow your mind. We found black holes that are pushing right up against that limit. They're not just fast, they're impossibly fast. And the implications of that fact are going to occupy our thoughts for the next several hours. Let me paint you a picture of just how extreme these spins are. The fastest spinning black hole we've confirmed is one called GRS 1915 plus 105, discovered in 1992. This stellar mass black hole, meaning it formed from a collapsed star, has a spin parameter of approximately 0.95 to 0.98. At its event horizon, the actual surface of the black hole, matter is moving at speeds between 95% and 98% of the speed of light. That's roughly 180,000 miles per second. To put that in perspective, light can travel around the Earth's equator 7.5 times in 1 second. This black hole's surface is rotating almost that fast. But wait, it gets crazier. Remember that supermassive black hole I mentioned at the beginning, NGC 1365? That beast is about 2 million times the mass of our Sun, and it's spinning at about 84% the speed of light. Now, because it's so much more massive, its event horizon is much larger, about 6 million miles across. That means the outer edge of the black hole is traveling at hundreds of thousands of miles per second, and it's dragging all the space-time around it along for the ride. Think of it like this. If our Sun were suddenly replaced by a rapidly spinning black hole of the same mass, don't worry, it won't happen. The orbit of Earth wouldn't change. Gravity doesn't work differently just because something's a black hole. But here's the thing. If you could somehow fly a spacecraft close to that black hole, you would notice something bizarre. Even if you tried to remain perfectly still, you would start to slowly orbit the black hole anyway. Not because of gravity pulling you in, but because the space-time you're sitting in is being dragged around the black hole. You're not moving through space itself, is moving beneath you. This is frame dragging, and it's one of the most important concepts we need to understand before we can tackle the really deep questions. In 1918, just 2 years after Schwarzschild's solution, and long before Kerr's breakthrough, 2 Austrian physicists named Joseph Lenz and Hans Thirring predicted that any rotating mass would drag spacetime around it. But the effect is normally so tiny as to be almost unmeasurable. Earth drags spacetime too, but the effect is millions of times weaker than other gravitational effects. With black holes, though, frame dragging becomes extreme. Near a rapidly spinning black hole, spacetime is being twisted so severely that it creates a region called the ergosphere. And here's where things get really wild. Inside the ergosphere, nothing, not even light, can remain stationary. Everything, absolutely everything, must orbit the black hole. Space itself is being dragged around so fast that standing still is physically impossible. Imagine you're on a river, and the current is so strong that no matter how hard you swim against it, you're being carried downstream. Now imagine the river is space-time itself, and you're made of matter that must obey the laws of physics. That's the ergosphere. You're caught in a current of reality itself. Now, here's your first major mind-blown moment. Remember when I said light can't remain stationary in the ergosphere? That means photons, particles of light, are being dragged around the black hole. But light always travels at the speed of light. It can't go faster or slower. So what happens when space-time itself is being dragged around faster than light can escape? The answer leads us to one of the most bizarre and wonderful predictions in all of physics. But before we get there, I need you to really understand what we mean when we say a black hole spins, because this is going to become crucial in about 10 minutes when we start talking about the Penrose process and how black holes can actually create energy. A spinning black hole isn't like a spinning ball. Remember, a black hole is a singularity, a point of infinite density where all the mass is concentrated. So what's actually spinning? The answer is, the space-time around the singularity is spinning. The black hole's mass and angular momentum warp space-time into a rotating configuration. It's not that there's a solid object rotating. It's that the geometry of space-time itself has a rotational structure built into it. Here's an analogy. Think of a whirlpool in water. The water is spinning, creating a vortex. But there's no solid object at the center spinning. The spinning is a property of the water itself, of the flow pattern. Now replace the water with space-time and make the whirlpool so intense that nothing can escape from it once it gets too close. That's a spinning black hole. And here's something that's going to set up our next major revelation. Because space-time itself is rotating, there's energy in that rotation. Massive amounts of energy. In fact, up to 29% of a black hole's total mass energy can be stored in its rotation. For a supermassive black hole weighing millions or billions of solar masses, that's an absolutely staggering amount of energy. And in 1969, a brilliant British physicist named Roger Penrose, who would win the Nobel Prize in 2020, figured out a way to extract that energy. Are you still with me? Because we're about to go deeper. We've laid the foundation. Black holes can spin. They spin fast. They drag space-time around them. And their spin contains enormous energy. Now we need to understand why some black holes spin near the speed of light, while others barely spin at all. And to understand that, we need to understand how black holes are born and how they grow throughout their lives. Let's talk about stellar black holes, first the ones formed from collapsed stars. When a massive star reaches the end of its life, it's been fusing hydrogen into helium, then helium into carbon, carbon into oxygen, and so on up the periodic table. But when it starts fusing iron, disaster strikes. Iron fusion consumes energy instead of producing it. The star's core, which has been supported against collapse by the outward pressure of fusion energy, suddenly has nothing holding it up. What happens next is catastrophically fast. The core collapses in less than a second. Electrons are crushed into protons, forming neutrons and releasing enormous numbers of neutrinos. If the core is massive enough more than about 3 times the mass of the Sun, not even neutron degeneracy, pressure can stop the collapse. The core keeps collapsing, crushing past the point where neutrons can exist, past the point where quantum mechanics can offer any resistance, until it collapses into a singularity. A black hole is born. But here's the key. That star was rotating before it collapsed. All stars rotate. Our sun rotates once every 27 days. Massive stars often rotate much faster. When the core collapses, conservation of angular momentum means the black hole it forms must be spinning. And because the mass has been compressed into a much, much smaller space, the rotation rate increases dramatically. Think about that pizza dough again. A massive star might have a core that's thousands of miles across, rotating once every few hours. When that core collapses to a black hole just a few miles across, the rotation speed increases by a factor of millions. Suddenly, you have a black hole that might be spinning dozens or even hundreds of times per second. In 2016, when LIGO detected gravitational waves for the first time, confirming Einstein's century-old prediction, they were detecting the merger of 2 black holes. And one of the things they measured was the spin of those black holes before and after the merger. The 2 black holes that collided had masses of about 36 and 29 solar masses, and they were both spinning moderately fast. When they merged, they created a single black hole of about 62 solar masses. Yes, 3 solar masses worth of energy was radiated away as gravitational waves, and that final black hole was spinning at about 67% of the maximum possible rate. That's important. Pay attention to that number, 67%. Not 99%, not 95%, just 67%. And that tells us something crucial. Black holes formed from stellar collapse don't automatically spin at near light speeds. They spin fast, sure, but not impossibly fast. So where do the ultra-fast spinning black holes come from? The answer lies in how black holes grow after they form. And this is where things get really interesting. Imagine a black hole sitting in space, minding its own business. Now imagine it has a companion star orbiting nearby. Over millions of years, the black hole's gravity pulls matter from that companion star. Gas streams from the star toward the black hole, but it doesn't fall straight in. Remember, the star and the black hole are orbiting each other, so the gas has angular momentum. It's moving sideways as well as inward. What forms is called an accretion disk, a swirling disk of superheated gas spiraling into the black hole. And here's the crucial part. That gas carries angular momentum. As it falls into the black hole, it transfers its angular momentum to the black hole, making it spin faster. It's like a cosmic flywheel, with matter constantly spinning up the black hole's rotation. But there's a catch. If the matter is falling in randomly from all directions, some of it will add angular momentum in one direction, some in the opposite direction, and they'll cancel out. For a black hole to spin up to extreme speeds, the accretion has to be organized. The matter needs to consistently add angular momentum in the same direction, and that requires something special. This is where we start to see the distinction between different types of black holes and different spin rates. Stellar black holes that form from collapsed stars and then sit relatively isolated in space will keep whatever spin they were born with. They might spin fast, maybe 40% to 70% of the maximum, but they don't spin up further because they're not accreting much matter. But black holes in binary systems, ones with companion stars constantly feeding them, can spin up over time. The accretion disk naturally organizes the matter into a coherent flow, all orbiting in the same direction. Over millions of years, this can spin the black hole up to incredible rates. And that's where we get black holes like GRS 1915 plus 105, spinning at 95% to 98% of the maximum. Now here's where supermassive black holes come into play, and this is going to lead us into some truly mind-bending territory. Supermassive black holes, the ones that lurk at the centers of galaxies, with masses of millions or billions of suns, have a different growth story. And understanding that story is going to help us understand why some of them spin so incredibly fast. Supermassive black holes are strange beasts. We still don't fully understand how they form. They're too massive to have come from single-star collapse. The current thinking is that they formed in the early universe from either the direct collapse of massive gas clouds or from the merger of many smaller black holes, and then they grew by accreting gas and swallowing stars over billions of years. Here's the thing. Supermassive black holes sit at the centers of galaxies, and galaxies are full of gas, and stars all orbiting in roughly the same direction. That means the accretion onto supermassive black holes is highly organized. Gas falls in preferentially from one direction, consistently adding angular momentum. Over billions of years, this can spin up a supermassive black hole to extreme rates. And we've observed this. In 2013, NASA's new STAR space telescope, working with the European Space Agency's XM Manhattan, measured the spin of NGC 1365's central black hole. They did this by observing the iron emission line from the accretion disk. Because spacetime is so warped near the spinning black hole, the iron emission line is distorted in a very specific way. By measuring that distortion, they could calculate the black hole's spin, about 84% of the maximum. But wait, if NGC 1365 is spinning at 84%, and we found stellar black holes spinning at 98%, that means the stellar black holes are spinning faster than some supermassive ones. Why would that be? And this question is going to lead us into one of the most fascinating aspects of black hole spin. It's not just about how fast they spin up. It's also about how they can spin down. Here's something that's going to surprise you. Black holes can lose angular momentum. And understanding how is crucial to understanding the full picture of black hole spin. Remember when I said that black holes in binary systems accrete matter in an organized way? Well, it turns out that's not always true. If a black hole swallows a star or another black hole that's orbiting in the opposite direction retrograde. As we call it, that merger actually removes angular momentum from the black hole. It's like a figure skater catching a weight that's moving in the opposite direction to their spin. It slows them down. This happens. In 2015, LIGO detected a black hole merger where one of the black holes was spinning in a direction misaligned with the orbital plane. These kinds of mergers can actually spin black holes down rather than up. And this might explain why not every black hole we observe is spinning at maximum rates. But here's the really interesting part. There's a tug of war happening. Organized accretion tries to spin black holes up. Retrograde mergers and accretion try to spin them down. The final spin of any particular black hole is the result of its entire life history. Every merger, every accretion event, every interaction it's ever had. And this leads us to a profound realization. The fastest spinning black holes are the ones that have had the most organized, prograde accretion throughout their lives. They're the ones that have been fed consistently from the same direction, building up angular momentum over millions or billions of years. They're the lucky ones, if you can call a black hole lucky. Now, we're about 40 minutes in, and I want to make sure you're still engaged because we're about to transition from understanding why black holes spin to understanding what happens when they spin that fast. And this is where things get truly bizarre. But before we do that, if you're enjoying this deep dive into one of the universe's most extreme phenomena, hit that like button. And if you haven't subscribed yet, what are you waiting for? We've got 3.5 hours left, and I promise you, the payoff is going to be absolutely worth it. Let me ask you a question. What's the fastest thing in the universe? You're probably thinking, the speed of light. And you'd be right. Nothing can move through space faster than light. Einstein proved that. It's a fundamental speed limit built into the fabric of reality. But here's the thing that's going to bend your brain. While nothing can move through space faster than light, space itself has no speed limit. Space can expand, contract, or move at any speed whatsoever. And that's exactly what's happening near a spinning black hole. Space-time itself is being dragged around at speeds that can exceed the speed of light. Wait, what? Did I just say space-time moves faster than light? Yes, I did. And it's completely consistent with relativity. Because the rule is, nothing can move through space-time faster than light, but space-time itself? That can do whatever it wants. Think of it this way. Imagine you're on a moving walkway at an airport, and you're walking forward at your maximum walking speed. The walkway is also moving forward. To someone standing still watching you, you appear to be moving faster than you could walk on your own. The walkway isn't making you move faster. It's moving, and you're moving on top of it. The same thing happens with light near a spinning black hole. Light travels at its usual speed through spacetime, but if spacetime itself is being dragged around the black hole, the light gets carried along for the ride. Now, let's talk about what this means in practice. Near a rapidly spinning black hole, there are actually two event horizons, not one. There's an inner event horizon and an outer event horizon, and between them is a region called the Cauchy horizon. But for our purposes, the important boundary is the outer event horizon combined with something called the ergosphere. The ergosphere, as I mentioned before, is the region where spacetime is being dragged around so fast that nothing can remain stationary. The outer boundary of the ergosphere is called the static limit. Outside the static limit, you can in principle stay still. Inside it, you must move. You're caught in the current. Here's what's wild. The ergosphere exists outside the event horizon. That means you can enter the ergosphere, experience the bizarre physics of frame dragging, and still escape. You're not doomed once you cross the static limit. You are doomed once you cross the event horizon. But between the static limit and the event horizon, there's this weird region where space-time is being twisted into pretzels, but escape is still possible. And this brings us to one of the most incredible ideas in all of physics, the Penrose process. In 1969, Roger Penrose realized something extraordinary. He figured out that if you drop an object into the ergosphere and then split it into two pieces, with one piece falling into the black hole and the other piece escaping, the escaping piece could have more energy than the original object. In other words, you could extract energy from the black hole's rotation. Here's how it works. Imagine you drop a spacecraft into the ergosphere. The frame dragging causes the spacecraft to orbit the black hole, giving it kinetic energy. Now you split the spacecraft into two parts. One part falls into the event horizon, carrying negative energy and negative angular momentum from the black hole's perspective. The other part slingshots out, carrying more energy than the original spacecraft had. You've extracted rotational energy from the black hole. This isn't science fiction. This is real physics. And here's the kicker. This might actually be happening naturally around spinning black holes. The jets of matter and energy that we observe shooting out from the poles of many black holes' jets that can extend for thousands or even millions of light years might be powered by the Penrose process or related mechanisms that extract rotational energy from the black hole. In fact, in 1977, two physicists named Roger Blandford and Roman Znayak proposed a mechanism by which magnetic fields threading through a spinning black hole's ergosphere could extract rotational energy and channel it into those jets. This is now called the Blandford-Znayak process, and it's one of the leading explanations for how quasars, the brightest objects in the universe, are powered. Think about that for a moment. The brightest objects in the entire universe, quasars that outshine entire galaxies, might be powered by the rotation of supermassive black holes. The spin of these cosmic monsters is literally lighting up the universe. Now here's your second major mind-blown moment. If black holes can spin down by transferring their rotational energy to jets and outflows, why do we still find black holes spinning at near maximal rates? Why haven't they all spun down to slower speeds? The answer is that they're constantly being spun back up by accretion. It's a balance. The black hole spins down by powering jets, and it spins back up by accreting matter. And the black holes we observe spinning at 95% to 99% of the maximum are the ones where this balance has favored spin-up. They've been fed more than they've been drained. But here's where things get really interesting, and this is going to set up the next major section of our journey. There's a theoretical limit to how fast a black hole can spin, and it's set by the physics of the event horizon itself. This is called the extremal limit, where the spin parameter A equals exactly 1. At this limit, something bizarre happens. The inner and outer event horizons meet. The black hole becomes what's called an extremal black hole, and its properties are, well, they're so weird that we're not even sure extremal black holes can exist in nature. An extremal black hole would have zero surface gravity at its event horizon. That means time dilation would become infinite. And here's the really weird part. An extremal black hole might have a naked singularity, a singularity that's not hidden behind an event horizon. And that would violate what's called the cosmic censorship hypothesis, which basically says that singularities should always be hidden inside black holes where we can't see them. Roger Penrose proposed the cosmic censorship hypothesis in 1969. The same year, he came up with the Penrose process. He argued that naked singularities without event horizons, probably can't exist in nature because they would lead to breakdowns in predictability. If you could see a singularity, you could observe its effects, and since singularities are places where physics breaks down, that would mean physics itself would break down in an observable way. That would be bad. Very bad. So the cosmic censorship hypothesis says nature has a way of preventing extremal black holes from forming. And Kip Thorne's limit, that black holes probably can't spin faster than about 99.8% of the maximum, is one proposed mechanism. As a black hole approaches extremal spin, it becomes increasingly difficult for it to accrete matter in a way that would push it over the edge. But, and this is important, we don't know for sure that extremal black holes can't exist. It's a hypothesis, not a proven theorem. And in fact, some of the black holes we've observed are spinning dangerously close to that limit. GRS 1915 plus 105 and 98% of maximum is pushing the boundaries. If we ever confirmed a black hole spinning at 99.9% or higher, it would raise serious questions about cosmic censorship. Now, let me take a moment to connect what we've talked about so far. We started with the question, why do some black holes spin near the speed of light? And we've built up an answer. They spin fast because they're born spinning from the collapse of rotating stars. And they spin even faster when they accrete matter in an organized way that consistently adds angular momentum. The fastest spinning black holes are the ones that have had stable prograde accretion throughout their lives. But first, let's take a moment to appreciate how far we've come in understanding these objects. In 1916, Schwarzschild discovered the mathematical possibility of black holes. For decades, they were considered mathematical curiosities, probably not real. Then, in the 1960s, we discovered quasars and started to suspect that supermassive black holes might exist at the centers of galaxies. In the 1970s, Cygnus X1 became the first strong candidate for a stellar black hole. And now, in the 21st century, we've directly detected gravitational waves from black hole mergers. We've imaged the shadow of a black hole with the Event Horizon Telescope. And we've measured the spins of dozens of black holes across the universe. We've gone from maybe they exist to we can measure them in just over a century. That's extraordinary progress. And it tells us something important. These aren't just abstract mathematical constructs. Black holes are real, physical objects, and their spins are real, measurable properties. Okay, we're about an hour in. Are you still with me? If you are, drop a comment and let me know what's blown your mind the most so far. Is it the frame dragging? The Penrose process? The fact that black holes can spin down as well as up? I want to know what's resonating with you. And if you haven't liked and subscribed yet, now is a great time. We're about to go even deeper into some truly mind-bending territory. Let's talk about what it would actually be like to approach a spinning black hole. Because this is where the abstract mathematics becomes something we can almost visualize. Almost. Imagine you're in a spacecraft approaching a black hole from a safe distance. Let's say it's a stellar mass black hole, about 10 times the mass of the Sun, spinning at 95% of the maximum. At this distance, let's say a few thousand miles away, things seem relatively normal. The black hole's gravity is strong, pulling you inward, but your spacecraft's engines can counteract that pull. You're in a stable orbit. But now you start to notice something strange. You're trying to orbit the black hole in a circle, maintaining a constant distance. But you find that your orbit is slowly precessing, the orientation is changing. It's like you're trying to drive in a straight line, but the road beneath you is slowly rotating. That's frame dragging. Even out here, thousands of miles from the event horizon, space-time is being twisted by the black hole spin. As you get closer, the frame dragging gets stronger. At about 5 times the Schwarzschild radius, remember, that's the radius of the event horizon for a non-rotating black hole, you cross into the ergosphere. And suddenly, things get really weird. Your spacecraft's orientation starts to twist. Even if you're not firing your engines, you start to rotate. Space-time itself is rotating, and you're being carried along. You try to hover in place, keeping the black hole directly below you, but you find it's impossible. No amount of thrust can keep you stationary. You must orbit. The current of space-time is too strong. But here's the thing. You can still escape. You're inside the ergosphere, but you're outside the event horizon. If you fire your engines and accelerate in the right direction, you can fight your way back out. It'll take a lot of fuel, but it's possible. Now let's say you keep going deeper. You're falling toward the event horizon, and the frame dragging is getting more intense. The black hole beneath you isn't a perfect sphere anymore. It's flattened at the poles, bulging at the equator. The faster a black hole spins, the more oblate it becomes. At maximum spin, the event horizon would be a really pronounced ellipsoid. And then you see something that makes your heart skip a beat, the photon sphere. This is a region where light can orbit the black hole. Photons traveling in just the right direction, at just the right distance, will circle the black hole forever, neither falling in nor escaping. For a spinning black hole, there are actually multiple photon spheres at different distances, depending on whether light is orbiting in the same direction as the black hole's spin, prograde, or opposite to it, retrograde. If you were at the photon sphere and you looked sideways, you could theoretically see the back of your own head. Light from the back of your head would orbit the black hole and come back to your eyes. Of course, you'd need impossibly good vision and timing, but theoretically, it's possible. Now you cross the event horizon, and here's where things get really strange. Remember, for a spinning black hole, the event horizon isn't the only point of no return. There's also that inner horizon I mentioned, the Cauchy horizon. And the space between the outer event horizon and the inner horizon is, well, it's a place where our understanding of physics starts to break down. Once you've crossed the outer event horizon of a spinning black hole, you might think you're doomed, just like with a non-spinning black hole. And you are doomed, don't get me wrong. But your doom is different. With a non-rotating Schwarzschild black hole, once you cross the event horizon, all paths lead to the singularity in your future. It's not a place you're falling toward. It's a moment in time you're falling toward. The singularity becomes part of your future, and you cannot avoid it any more than you can avoid tomorrow. But with a spinning Kerr black hole, things are weirder. The singularity isn't a point, it's a ring. A rotating ring of infinite density, zero size. And mathematically, technically, theoretically, if you could navigate the space between the inner and outer horizons correctly, you might be able to pass through the ring's singularity without touching it. Now, before you get excited about this as a possible survival strategy or a gateway to other universes, which is what some science fiction has proposed, let me hit you with reality. First, the inner region of a spinning black hole is probably catastrophically unstable. There's something called the mass inflation instability that physicists discovered in the 1990s. Basically, as you approach the inner horizon, the energy of infalling matter and radiation from the entire past history of the universe gets blue shifted to infinite values. You'd be hit by an infinite wall of energy. That's not survivable. Second, quantum effects almost certainly change the picture completely. We don't have a complete theory of quantum gravity. That's the holy grail of physics, combining general relativity with quantum mechanics. But whatever that theory looks like, it's going to tell us that the interior of black holes doesn't behave the way classical general relativity predicts. The inner horizon might not even exist. The ring singularity might not be a ring at all. But here's what's fascinating. The very fact that spinning black holes have these weird internal structures in our classical theories tells us something. It tells us that spin matters. It tells us that the rotation of black holes fundamentally changes their nature in ways that go beyond just their spinning. The geometry of spacetime inside and around a spinning black hole is qualitatively different from a non-spinning one. And this brings us to something that's going to blow your mind. Time and space swap roles inside the event horizon of a spinning black hole in ways that are even weirder than in a non-spinning black hole. Outside a black hole, we move freely through space, but are dragged inevitably forward in time. We can go left, right, forward, backward, up, or down, but we can only go forward in time. Inside the event horizon of a non-rotating black hole, one of those spatial directions becomes time-like. Specifically, the direction toward the singularity becomes time-like. You're being pulled toward the singularity the same way you're normally pulled toward the future. It's inevitable. But inside a spinning black hole, the frame dragging is so extreme that the direction around the black hole, the orbital direction, also becomes partially time-like. You're not just being pulled toward the singularity, or the ring singularity, in this case. You're also being dragged around it. And as you approach the inner horizon, things get even stranger. Some solutions to the equations suggest that closed time-like curves might exist paths through spacetime that loop back on themselves. Time travel, in other words? Now, let me be very clear. We have no idea if any of this is real. These are solutions to Einstein's equations, yes, but they're probably not physical. The instabilities I mentioned, plus quantum effects, probably prevent any of this from actually occurring. But the fact that the mathematics of spinning black holes allows for these possibilities tells us something profound. Extreme rotation does weird things to spacetime. Really weird things. And this is where we need to talk about one of the most important developments in black hole physics in the last 50 years, black hole thermodynamics. Because it turns out that black holes aren't just objects in spacetime. They're thermodynamic systems with temperature, entropy, and all the properties of normal matter. And the spin of a black hole affects its thermodynamic properties in crucial ways. In 1974, Stephen Hawking discovered something that shocked the physics world. Black holes radiate, they emit particles. They have a temperature. Now, this temperature is incredibly tiny for any realistic black hole, a stellar. Mass black hole has a temperature of about a 10 millionth of a degree above absolute zero. And a supermassive black hole is even colder. But it's not zero. Black holes glow. This is called Hawking radiation, and it comes from quantum effects near the event horizon. Virtual particle pairs are constantly popping into existence everywhere in space due to quantum uncertainty. Usually, they annihilate each other almost immediately. But near the event horizon of a black hole, one particle can fall in while the other escapes. The escaping particle becomes real, and it carries energy away from the black hole. The black hole loses mass. Over unimaginably long time scales, far longer than the current age of the universe, black holes will evaporate completely. But here's where spin comes in. A spinning black hole has a different temperature than a non-spinning one. And more importantly, a spinning black hole can radiate not just particles with energy, but particles with angular momentum. The black hole can spin down through Hawking radiation. It's like the quantum version of the Penrose process. And this leads to something profound that we're still trying to understand, the information paradox. When a black hole evaporates through Hawking radiation, what happens to all the information about everything that fell into it? Quantum mechanics says information can't be destroyed, but general relativity says anything that falls into a black hole is gone forever, with only the black hole's mass, charge, and spin remaining. This is called the no-hair theorem. Black holes have no hair, meaning no complex features, just those three numbers. But if Hawking radiation is purely thermal, purely random, then the information is lost when the black hole evaporates. And that violates quantum mechanics. This is the black hole information paradox, and it's been one of the central problems in theoretical physics for 50 years. The spin of the black hole is relevant because it's one of those three hairs, one of those three conserved quantities. When you throw a spinning object into a black hole, the black hole's spin changes to account for the angular momentum of what you threw in. That angular momentum is preserved. But what about all the other details of what you threw in? The colors, the shapes, the quantum states? Are they really lost forever? Recent developments, particularly from string theory and the holographic principle, suggest that information isn't lost. It's encoded in the Hawking radiation in extremely subtle correlations that we're just beginning to understand. And the spin of the black hole might play a crucial role in how that information is encoded and released. But we're getting ahead of ourselves. Let me bring this back to something more concrete. Because we're approaching the midpoint of our journey, and I want to make sure we're building understanding progressively. Let's talk about how we actually measure the spin of black holes, because this is where theory meets observation, and it's absolutely fascinating. There are several methods, and each one gives us a different window into black hole spin. The first and most direct method is called the X-ray reflection method. Here's how it works. Remember those accretion disks I mentioned? The superhot gas spiraling into the black hole? That gas emits X-rays, and those X-rays include specific emission lines from iron atoms in the disk. Now, here's the clever part. As the gas orbits the black hole, some of those X-rays shine down onto the black hole and get reflected back up. But the reflection happens from different parts of the accretion disk, some parts moving toward us, some moving away, some deep in the gravitational well, some farther out. Each location experiences different amounts of gravitational redshift, Doppler shift, and frame dragging effects. The result is that the iron emission line, which would normally be a sharp spike at a specific energy, gets smeared out into a broad, distorted shape. And the exact shape of that distortion depends on the spin of the black hole. Fast spin means strong frame dragging, means more distortion. By measuring the shape of the iron line, we can calculate the black hole's spin. This is exactly how they measured NGC 1365 spin at 84% of maximum. They used NASA's newest TAR telescope and ESASX Newton to observe the iron line, analyze its shape, and extract the spin parameter. The second method is called the continuum fitting method. The accretion disk has an iconic inner edge radius where the disk stops and the black hole begins. This is called the innermost stable circular orbit, or ISCO. Inside the ISCO, orbits are unstable, and matter spirals directly into the event horizon. Here's the key. The location of the ISCO depends on the black hole's spin. For a non-rotating black hole, the ISCO is at 3 times the Schwarzschild radius. But for a maximally spinning black hole, the ISCO can be as close as half the Schwarzschild radius 6 times closer. That means the accretion disk can get much closer to the black hole, and gas can orbit much faster, and the disk gets much hotter. By measuring the temperature profile of the accretion disk, how hot it is at different radii, we can figure out where the inner edge is. And from that, we can calculate the spin. This is how we measured the spin of black holes like GRS 1915 plus 105. The third method is the newest and most exciting: gravitational waves. When two black holes merge, they emit gravitational waves ripples in space-time itself. And the pattern of those waves depends on the masses and spins of the black holes involved. LIGO and Virgo have now detected dozens of black hole mergers, and for each one, they've measured the spins of the merging black holes. And here's what's fascinating. The spins vary wildly. Some black holes are barely spinning. Some are spinning at 70% or 80% of maximum. A few might be spinning faster. And the distribution of spins tells us about the formation history of these black holes. For example, if two black holes formed in a binary system from two stars that lived and died together, their spins should be aligned with each other and with the orbital plane. But if they formed separately and came together later, their spins could be randomly oriented. By looking at the spin distributions across many mergers, we can piece together the story of how black holes form and evolve in the universe. And here's something that's going to set up our next section. In 2020, LIGO detected something extraordinary. They observed a merger between a black hole and a neutron star, the first confirmed observation of such an event. The black hole had a mass of about 9 solar masses and was spinning moderately fast. When it swallowed the neutron star, we witnessed a black hole consuming matter and potentially spinning up in real time. Well, not quite real time. The event happened about 900 million years ago, and the gravitational waves just reached us. But still, We witnessed the process. Now we're about 90 minutes in, and this is where I want to pivot. We've been talking a lot about the physics, the equations, the measurements, the mechanisms. But I want to take a moment to connect this to something deeper, something personal. Because the question, why do some black holes spin near the speed of light, isn't just a physics question. It's a question about the nature of our universe, about the fundamental laws that govern reality, and ultimately, about our place in all of this. Think about what we've discovered. We live in a universe where matter can collapse so completely that it tears a hole in spacetime. We live in a universe where those holes can spin so fast that they drag reality itself around them. We live in a universe where the brightest lights quasars visible across billions of light years are powered by the spin of invisible monsters. And here's what gets me. We figured this out. Humans, sitting on a rock orbiting an average star in an unremarkable galaxy, used mathematics and observation to understand some of the most extreme phenomena in the entire cosmos. We can't visit these black holes. We can't touch them or see them directly, but we can understand them. Karl Schwarzschild, dying of an autoimmune disease on the Russian front in 1916, solved Einstein's equations by hand with pencil and paper. Roy Kerr, working with mid-20th century mathematics, found the exact solution for a spinning black hole, a problem so difficult that Einstein himself didn't think it could be solved. Roger Penrose, with pure thought, realized that you could extract energy from a black hole spin. Stephen Hawking, despite his physical limitations, discovered that black holes radiate and evaporate. These people looked at symbols on paper equations, numbers, abstract mathematics, and saw the truth about objects so extreme that they bend spacetime into knots. That's extraordinary. That's beautiful. That's what it means to be human. And you, watching this video right now, whether you're in Tokyo or London or New York or Mumbai or São Paulo or anywhere else, you're part of that same endeavor. You're engaging with these ideas. You're trying to understand. You're exercising the same capacity for abstract thought that allowed those physicists to peer into the hearts of black holes. So when I ask, why do some black holes spin near the speed of light? I'm not just asking about angular momentum and accretion disks. I'm asking, what does this tell us about the universe we inhabit? What does it mean that reality allows for such extremes? And here's my answer. It tells us that the universe is far stranger, far more subtle, far more surprising than our everyday intuition suggests. The speed of light seems fast until you realize that black holes can drag spacetime around at speeds that make light look slow. Gravity seems simple until you realize it's not a force pulling you down, it's the curvature of spacetime telling you how to move. Matter seems solid until you realize it can collapse into a point of infinite density. Every comfortable assumption we have about reality is challenged by the existence of spinning black holes. And that should fill us with wonder. It should make us humble. And it should make us curious. Because here's the thing, we don't know everything. Not even close. We've figured out a lot, how black holes form, how they spin, how they radiate, but there's so much we don't know. We don't know what happens at the singularity. We don't know how to reconcile quantum mechanics with general relativity. We don't know if cosmic censorship always holds. We don't know if information is truly preserved in black hole evaporation. Every answer we find raises new questions. And that's not a bug, it's a feature. That's how science works. That's how understanding deepens. Now, let me ask you something. Are you starting to see black holes differently? When you started watching this video, maybe you thought of black holes as cosmic vacuum cleaners, sucking up everything around them. Maybe you thought they were simple objects, just massive, dark, and dangerous. But now you know they're not simple at all. They're dynamic. They spin. They radiate. They drag space-time. They power the brightest objects in the universe. They preserve angular momentum and maybe even information in quantum correlations we're just beginning to understand. Black holes aren't just objects in the universe. They're laboratories for testing the fundamental laws of physics. They're places where general relativity and quantum mechanics collide. They're the universe's way of showing us that reality is far richer than we ever imagined. And the fastest spinning ones, the ones pushing right up against the theoretical limits, those are the most extreme laboratories of all. They're testing the boundaries of what's possible. They're asking, how far can you spin spacetime before it breaks? How much energy can you pack into rotation? What happens at the absolute limit? We don't have all the answers yet, but we're working on it. And that brings me to something I want you to really internalize. This is happening right now. The study of spinning black holes isn't ancient history. It's cutting-edge, ongoing research. Right now, as you're watching this, there are teams of scientists around the world analyzing data from LIGO and Virgo, detecting new black hole mergers, measuring new spins. There are astronomers pointing X-ray telescopes at distant galaxies, measuring iron emission lines, calculating spin parameters. There are theorists working on equations, trying to understand the quantum structure of event horizons, trying to solve the information paradox. In 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow, the supermassive black hole at the center of the galaxy M87. And one of the things they're working on now is measuring that black hole's spin from the shape and asymmetry of the shadow. The results aren't published yet, but when they are, we'll have another data point, another measurement, another piece of the puzzle. And here's something that should excite you. Future detectors like LISA the laser, interferometer space antenna, will be able to detect gravitational waves from supermassive black hole mergers. We're talking about black holes millions or billions of times more massive than our sun, colliding and merging, spinning up or spinning down. LISA will measure their spins with unprecedented precision. It's scheduled to launch in the 2030s, and when it does, it's going to revolutionize our understanding of supermassive black hole spin. So when you're thinking about the question, why do some black holes spin near the speed of light? Remember, we're still figuring it out. We have a good understanding of the basic mechanism. Stellar collapse preserves angular momentum, accretion spins black holes up, retrograde mergers spin them down. We understand frame dragging, ergospheres, the Penrose process. We can measure spins using X-rays and gravitational waves. But there are still mysteries. Why do some stellar black holes spin so much faster than others? What determines whether a black hole in a binary system spins up or down over time? How close to the extremal limit can black holes really get? What happens to the spin when a black hole completely evaporates through Hawking radiation? These are open questions. And some of you watching this, if you're young enough, if you're inspired enough, might be the ones to answer them. You might be the next Roy Kerr or Roger Penrose or Kip Thorne. You might be the one who figures out quantum gravity and resolves the information paradox. You might be the one who discovers a black hole spinning at 99.99% of maximum and has to figure out how it got that way. And even if you don't become a physicist, even if you never publish a paper on black hole spin, you're still part of this because you're engaging with these ideas. You're letting them change how you see the universe. You're exercising your capacity for wonder, and that matters. Okay, let me shift gears a bit because we're about 2 hours in, and I want to explore some of the weirder implications of rapidly spinning black holes. Implications that touch on everything from the possibility of time travel to the ultimate fate of the universe. Let's start with something that sounds like pure science fiction, but is actually grounded in real physics. The possibility of using spinning black holes as energy sources. Remember the Penrose process? The idea that you can extract rotational energy from a black hole by dropping objects into the ergosphere. Well, some physicists have seriously considered whether advanced civilizations could use this as a power source. Here's how it might work. You build a civilization around a rapidly spinning black hole. You drop garbage, waste matter, anything you don't need into the ergosphere in precisely calculated trajectories. That matter splits part, falls into the black hole. Part escapes with more energy than it had before. You capture that energy and use it to power your civilization. This isn't just speculation. In 1971, a physicist named John Wheeler, who coined the term black hole, by the way, worked out the details. He showed that you could theoretically extract up to 29% of a black hole's rest mass energy through the Penrose process if the black hole is spinning at maximum rate. That's 29% of mc. For a black hole with the mass of the Sun, that's more energy than the Sun will produce through fusion over its entire 10 billion year lifetime. And it gets wilder. In 1977, Roger Blandford and Roman Znayak showed that you could potentially extract even more energy if you use magnetic fields instead of physical matter. A spinning black hole threaded with magnetic field lines acts like a giant dynamo, converting rotational energy into electromagnetic energy that can be channeled into jets. This might actually be what's powering quasars and active galactic nuclei, natural examples of the Penrose-Blandford-Znayak process extracting energy from spinning supermassive black holes. We're talking about objects outputting more energy per second than 1 trillion suns, all from black hole spin. Now, here's where it connects to our original question. If extracting energy from spinning black holes is this efficient, why aren't all black holes spun down to zero? Why do we still observe black holes spinning at 95% or 98% of maximum? The answer has to do with timescales and balance. Black holes lose rotational energy through jets and Hawking radiation, yes, but they gain it back through accretion. And in the environments where we find the fastest spinning black holes binary systems with companion stars, galactic centers with plentiful gas, the accretion is constant and efficient. It's like trying to drain a bathtub while the faucet is running. If the faucet is pouring water in faster than the drain can let it out, the tub stays full. Similarly, if accretion is adding angular momentum faster than jets and radiation can remove it, the black hole stays spinning fast. But there's a twist, and this is going to lead us into some deep philosophical territory. Eventually, in the far, far future, trillions upon trillions of years from now, the universe will run out of matter to accrete. Stars will stop forming, galaxies will go dark, and black holes will be left alone in the void, slowly evaporating through Hawking radiation. As a black hole evaporates, it radiates away both mass and angular momentum. It spins down. Over timescales that make the current age of the universe seem like an eye-blink 10,100 years or more even, the largest supermassive black holes will evaporate completely. They'll spin down to nothing, then evaporate to nothing, until finally there's nothing left but a burst of radiation. And then, well, then the universe will be a cold, dark, expanding void. Nothing but photons and other massless particles, spreading out forever, getting colder and more diffuse. This is called the heat death of the universe, and it's the most likely ultimate fate according to our current understanding of cosmology. But here's what strikes me as profound. The fastest spinning black holes we observe today, the ones pushing 98% of the speed of light, are living their most intense lives right now. Right now, in this era of the universe, when there's still matter to accrete, still stars to swallow, still angular momentum to gain. Billions of years from now, they'll slow down. Trillions of years from now, they'll be alone. And incomprehensibly far in the future, they'll be gone. We're living in the vibrant youth of the universe, when things are still happening, when black holes are still spinning fast, when stars are still shining. And that's kind of special, isn't it? Now, let me take you somewhere even stranger. Let's talk about the possibility, however remote, that rapidly spinning black holes might allow for travel to other universes. Remember when I mentioned that the mathematics of spinning black holes allows for closed time-like curves and possibly traversable paths Through the ring singularity? Well, some solutions to Einstein's equations suggest that if you could somehow navigate through a spinning black hole without being destroyed, you might emerge into a different region of spacetime. Maybe even a different universe. This is pure speculation. Let me be clear. The interior of a real black hole probably doesn't behave like the idealized mathematical solutions suggest. Quantum effects, instabilities, infinite energy densities. All of these probably make it impossible. But the mathematics hints at possibilities. And here's why that's interesting. It tells us that general relativity, our best theory of gravity, allows for such strange connections in spacetime. The math doesn't forbid them. Nature might forbid them through mechanisms we don't fully understand yet, but the underlying theory permits them. What does that mean? It means that spacetime is even more flexible, even more malleable than we usually think. It means that extreme rotation can do things to spacetime that we're only beginning to glimpse. And this connects to something deep about physics, the relationship between what's mathematically possible and what's physically real. Not everything that's mathematically consistent actually exists in nature. There might be solutions to Einstein's equations that describe spacetimes that simply can't occur. But figuring out which solutions are physical and which aren't, that requires understanding quantum gravity, and we're not there yet. So when we study the fastest spinning black holes, we're probing that boundary between mathematical possibility and physical reality. We're asking, how extreme can nature get? What are the real limits? And every measurement we make, every spin parameter we calculate, every gravitational wave we detect is another data point helping us answer that question. Now, let's talk about something that connects directly to you, to your everyday life, to your understanding of reality. Because I want to make sure this isn't just abstract physics. I want you to feel how this knowledge changes your worldview. Here's a question. What does it mean that objects exist in our universe that spin so fast they break our intuitions about time and space? Think about your experience of reality. You move through space freely left, right, forward, backward. But you move through time in only one direction forward, at 1 second per second. Space and time seem completely different, completely separate. But general relativity tells us they're not separate. They're unified into spacetime, a four-dimensional fabric that can be bent, stretched, twisted, and torn. And nowhere is this more obvious than near a spinning black hole, where the distinction between space and time becomes blurred, where you can't remain still in space because space-time itself is moving. This should mess with your head. It should make you question your basic intuitions about reality. Because your intuitions are based on your everyday experience in a weak gravitational field, moving slowly compared to the speed of light. But that's not the full picture. That's just a special case. The full picture includes black holes spinning at 98% of the speed of light, dragging space-time into spirals, creating regions where time and space swap roles. And that full picture is reality, the universe we actually live in. So when you go about your daily life driving to work, eating lunch, scrolling through your phone, remember, you're living in a universe that contains these extremes. You're living in a universe where the fabric of reality can be twisted into knots. You're living in a universe far stranger than it appears. And here's what's beautiful. You now know this. You understand, at least conceptually, that rapidly spinning black holes exist, that they drag space-time, that they power quasars, that they preserve angular momentum across billions of years. You understand things that 99.9% of humans who have ever lived couldn't have understood, because the knowledge didn't exist yet. You're living in an extraordinary time. A time when we can detect gravitational waves from black hole mergers billions of light years away. A time when we can image the shadow of a black hole. A time when we can measure spin parameters to 2 decimal places. And this is just the beginning. In your lifetime, we're going to learn so much more. We're going to detect supermassive black hole mergers with LISA, we're going to image more black hole shadows with next-generation telescopes. We might even develop a complete theory of quantum gravity and finally understand what happens at the singularity. You get to witness this. You get to be part of the generation that goes from black holes are theoretical curiosities to we understand black holes in exquisite detail. That's a privilege. Now, we're approaching the 3-hour mark, and I want to spend the remaining time going even deeper into some specific aspects that we've touched on but haven't fully explored. We're going to talk about the relationship between black hole spin and cosmic structure formation. We're going to talk about primordial black holes and whether they might be spinning. We're going to talk about the role of magnetism in black hole spin. And we're going to tie it all together with a perspective on what black hole spin tells us about the deep nature of physical law. But before we do that, if you've made it this far, seriously, thank you. Drop a comment and let me know. Tell me what's been your favorite part. Tell me what questions you still have. And if you haven't subscribed yet, what are you waiting for? This is the kind of deep, thorough exploration of fascinating topics that I want to keep doing, and your subscription helps make that possible. All right, let's talk about black holes and cosmic structure. Because the spin of black holes doesn't just tell us about the black holes themselves, it tells us about the environments they form in and the evolution of galaxies over cosmic time. Here's something fascinating. The spin of supermassive black holes at the centers of galaxies seems to be correlated with the properties of those galaxies. Galaxies with more organized, coherent gas flows tend to have faster spinning black holes. Galaxies with more chaotic, disordered gas tend to have slower spinning black holes. Why? Because, as we discussed, black holes spin up when they accrete matter coherently from one direction, and they spin down or don't spin up as much when they accrete chaotically from many directions. So the spin of a supermassive black hole is a record of its accretion history, which is in turn a record of the galaxy's history. In 2015, a team of astronomers published a study looking at the correlation between black hole spin and galaxy type. They found that black holes in elliptical galaxies, which formed from chaotic mergers of smaller galaxies, tend to spin more slowly. Black holes in spiral galaxies, which have more organized gas flows, tend to spin faster. This tells us something profound. You can't understand black holes in isolation. They're embedded in galaxies. They're fed by galaxies. Their spins are determined by galactic evolution. And in turn, their jets and outflows affect galactic evolution by heating gas, triggering or suppressing star formation, and regulating how galaxies grow. This is called AGN feedback, active galactic nucleus feedback, and it's one of the most important processes in cosmology. The spin of supermassive black holes, through the Blandford-Znaick process and related mechanisms, determines how much energy they can pump into their host galaxies. And that, in turn, determines whether those galaxies continue forming stars or become quiescent and red. So the question, why do some black holes spin near the speed of light, is intimately connected to the question, why do galaxies look the way they do? Fast-spinning black holes have different effects on their environments than slow-spinning ones. They pump energy out differently. They shape galaxy evolution differently. And here's where it gets even more interesting. Computer simulations of galaxy formation have to include black hole spin to get realistic results. If you simulate galaxies without accounting for how black hole spin affects jet power, you get galaxies that don't match observations. The simulations produce too many massive galaxies, or galaxies with the wrong colors, or gas distributions that don't make sense. But when you include black hole spin, when you model how accretion affects spin and how spin affects jets, suddenly the simulations start matching reality. You get galaxies that look like real galaxies. You get the observed correlation between black hole mass and galaxy properties. You get the right mix of star forming in quiescent galaxies at different epochs of cosmic history. This tells us that black hole spin isn't just a detail, a crucial ingredient in understanding how the universe evolved from the smooth, simple conditions of the Big Bang to the complex, structured universe we see today. Now let me take you in a different direction. Let's talk about primordial black holes, hypothetical black holes that might have formed in the very early universe, shortly after the Big Bang. If primordial black holes exist, and we're not sure they do, though some dark matter could be primordial black holes, they would have formed from density fluctuations in the extremely hot, dense early universe. And here's the question: would they be spinning? The answer depends on the initial conditions. If the density fluctuation that collapsed to form a primordial black hole had any net rotation at all, the resulting black hole would spin. But the early universe was incredibly chaotic, with quantum fluctuations creating density perturbations with random properties. Some would have had net rotation, some wouldn't. Computer simulations suggest that primordial black holes, if they exist, would have a wide range of spins. Some would be barely spinning, some would be spinning fast. The distribution would depend on the detailed statistics of the early universe's quantum fluctuations. And here's why this matters. If we ever detect primordial black holes, maybe through gravitational lensing, or by detecting gravitational waves from their mergers, measuring their spins will tell us about the early universe. It'll tell us about the statistical properties of quantum fluctuations shortly after the Big Bang. It'll be a window into the first fraction of a second of cosmic history. That's extraordinary. The spin of black holes isn't just about the black holes. It's a probe of the fundamental nature of the universe itself. Now let's talk about magnetism, because magnetic fields play a huge role in black hole spin. And we haven't discussed this in enough detail yet. Black holes themselves don't have magnetic fields. Remember the no-hair theorem. A black hole is characterized entirely by its mass, spin, and electric charge. And realistic black holes have essentially zero net charge. But the accretion disks around black holes are threaded with magnetic fields, and those fields can have enormous effects. Here's how it works. The gas in an accretion disk is ionized plasma-charged particles. As the plasma spirals into the black hole, it drags magnetic field lines with it. These field lines can connect the disk to the black hole, or stretch out along the rotation axis to create the jets we see. And here's the crucial part. Magnetic fields can transport angular momentum. As gas falls into the black hole through the disk, friction and magnetic stresses in the disk cause the gas to lose angular momentum. It's transferred outward through the disk. The inner gas spirals in, the outer gas spreads out, and the net result is that some of the system's angular momentum ends up being transferred to the black hole itself. This is actually one of the main mechanisms by which black holes spin up. It's not just that matter falls in carrying angular momentum. It's that the magnetic structure of the accretion disk efficiently funnels that angular momentum onto the black hole. And the jets? Those are powered by magnetic fields too. The Blandford's-Naik process, which I mentioned earlier, relies on magnetic fields threading through the ergosphere and extracting rotational energy. The magnetic field lines are twisted by the black hole's rotation, and this twisting accelerates charged particles to relativistic speeds, creating the jets. In 2019, the Event Horizon telescope collaboration didn't just image the shadow of M87's black hole, they also measured the polarization of the light from the accretion disk, which tells us about the magnetic field structure. And what they found was fascinating. The magnetic field near the black hole is extremely organized, with field lines running in coherent patterns. This organization is exactly what you'd need for efficient jet launching via the Blandford's-Naik process. And here's the kicker. The strength and organization of the magnetic field depends on how fast the black hole is spinning. A rapidly spinning black hole can maintain stronger, more coherent magnetic fields in its ergosphere. A slowly spinning black hole can't, so the spin directly determines how powerful the jets can be. This creates a feedback loop. Fast spin enables powerful jets, which extract rotational energy which slows the spin down. But fast spin also enables efficient accretion through magnetic torques, which spins the black hole back up. The final equilibrium spin is determined by this balance between jet power and accretion efficiency. And different black holes reach different equilibrium points depending on their environments. A black hole in a gas-rich environment with lots of accretion will spin up to very high speeds, maybe 95% or 98% of maximum. A black hole in a gas-poor environment with weak accretion will spin down to moderate speeds, maybe 40% or 50% of maximum. So when we observe a black hole spinning at 98% of the speed of light, we're observing a black hole that's in a special situation. It's being fed copiously and efficiently. The magnetic fields are organized, and the accretion has been sustained for millions or billions of years in roughly the same configuration. These are the lucky black holes, if you will. The ones in the right place, at the right time, to be spun up to extreme speeds. Now, let me connect this to something even deeper, the question of what physical laws allow these extremes. Physics is full of conservation laws. Energy is conserved, momentum is conserved, angular momentum is conserved. These laws are fundamental. They're not just descriptions of how things happen to behave. They're built into the structure of spacetime itself. Emmy Noether proved in 1915 that every symmetry of nature corresponds to a conservation law. Time symmetry gives us energy conservation. Space symmetry gives us momentum conservation. Rotational symmetry gives us angular momentum conservation. Black holes obey these laws absolutely. When matter falls into a black hole, the angular momentum doesn't disappear. It's added to the black hole's spin. When a black hole evaporates through Hawking radiation, the angular momentum is carried away by the emitted particles. The books always balance. But here's what's profound. These conservation laws constrain what's possible. They set limits. Angular momentum can't be created or destroyed, so a black hole can only spin as fast as the matter falling into it allows. And there are additional constraints from general relativity, the physics of the event. Horizon itself sets an upper limit on how fast a black hole can spin. The fact that we observe black holes spinning at 98% of the theoretical maximum tells us that nature is pushing right up against these fundamental limits. The universe is exploring the full parameter space of what's allowed. It's not content to stay in the safe middle ground. It's testing the boundaries. And that's true throughout physics. Particles are accelerated to within a tiny fraction of the speed of light in particle colliders. Stars form with masses ranging from barely massive enough to fuse hydrogen up to hundreds of times the mass of the sun. Neutron stars spin hundreds of times per second, right up against the point where they'd tear themselves apart. Nature explores extremes. And every time we study those extremes, we learn about the fundamental laws that govern reality. So why do some black holes spin near the speed of light? Because the laws of physics allow them to. Because angular momentum is conserved and must go somewhere when matter collapses or accretes. Because there are environments in the universe binary systems, galactic centers where accretion can be sustained and organized over millions of years. Because magnetic fields efficiently transport angular momentum. Because the equilibrium between spin-up and spin-down mechanisms happens to settle at very high spin rates in certain circumstances. But also because the universe is capable of creating and sustaining extremes. Because reality is far more rich and complex than our everyday experience suggests. Because the laws of physics, when pushed to their limits, produce phenomena that boggle the mind. Now we're getting close to the end of this journey, and I want to take a moment to zoom out and think about what all of this means. We started with a simple question. Why do some black holes spin near the speed of light? And we've built up an answer piece by piece. We learned about angular momentum conservation, stellar collapse, accretion disks, frame dragging, the ergosphere, the Penrose process, the Blandford's Nyack mechanism, Hawking radiation, gravitational waves, magnetic fields, and cosmic structure formation. We learned that black holes aren't static objects. They're dynamic, evolving, interacting with their environments. We learned that spin isn't just a number. It determines the geometry of spacetime, the power of jets, the efficiency of energy extraction, the fate of infalling matter. We learned that measuring black hole spin is hard, but possible, using X-ray spectroscopy, continuum fitting, and gravitational wave astronomy. We learned that the spins we measure tell us about formation mechanisms, accretion history, and galactic evolution. And we learned that the fastest spinning black holes, ones pushing 98% or 99% of the maximum, are the ones in special environments where everything came together just right to spin them up and keep them spinning. But beyond all the specific facts and mechanisms, I hope you've gained something deeper, a sense of wonder at the universe we inhabit, a sense of humility at the extremes nature can produce, and a sense of excitement at what we've learned and what we're still discovering. Because here's the thing, this isn't finished. Our understanding of black hole spin is still evolving. There are still open questions, still mysteries to solve. For example, what exactly happens at the Cauchy horizon inside a spinning black hole? Does quantum gravity prevent the instabilities that classical physics predicts? Or is there some other mechanism at play? What's the maximum spin a black hole can actually achieve in nature? Is it Thorne's limit of 99.8%? Or can they get even closer to extremal? And if a black hole did somehow reach exactly maximal spin, would cosmic censorship be violated? Would we see a naked singularity? How does black hole spin affect the merger dynamics when two black holes collide? Can we use gravitational wave observations to test general relativity in the strong field regime by measuring how spins processes and merge? What role did rapidly spinning black holes play in the early universe? Did their jets help ionize the intergalactic medium? Did they affect the formation of the first galaxies? And the big one, what's the quantum structure of the event horizon? How is information encoded in Hawking radiation? Does the spin of the black hole affect how information is preserved and released? These questions are at the frontier of physics, and answering them will require new observations, new theoretical insights, and new ways of thinking about spacetime, quantum mechanics, and the nature of reality itself. And maybe, just maybe, one of you watching this will contribute to those answers. Maybe you'll be the one who develops a better theory of quantum gravity. Maybe you'll be the one who analyzes LISA data and discovers a supermassive black hole spinning at 99.9% of maximum. Maybe you'll be the one who figures out how to extract energy from black hole spin for the benefit of future civilizations. Or maybe you'll do something completely different with your life, but you'll carry this knowledge with you. You'll know that the universe is stranger and more wonderful than it appears. You'll know that reality can be understood through observation and reason. You'll know that there are cosmic monsters out there, spinning faster than seems possible, dragging spacetime itself around them. And that knowledge will change how you see everything. Let me tell you why I think this matters. We live in a time when it's easy to be cynical, to think that humanity is small and insignificant, that nothing we do matters on cosmic scales. And in some ways, that's true, we are small. Earth is a tiny rock orbiting an average star in an unremarkable galaxy among hundreds of billions of galaxies. But here's what's also true. We understand black holes. We understand objects so extreme that they tear holes in spacetime, so massive that they bend light, so fast spinning that they drag reality itself into spirals. We understand them through mathematics, through observation, through the power of human reason. That's not insignificant. That's extraordinary. The fact that matter can organize itself into patterns, into atoms, molecules, cells, brains, people that can turn around and understand the universe they're part of. That's perhaps the most remarkable thing in all of existence. You are a pattern in the universe that can comprehend other patterns. You're made of atoms that were forged in stars, and you can understand how stars work. You're affected by gravity, and you can understand Einstein's field equations. You exist in space-time, and you can conceptualize how space-time can be warped and twisted. That's beautiful. That's meaningful. That's worth celebrating. So when you look up at the night sky, remember, out there, beyond what you can see, there are black holes spinning at 98% of the speed of light. There are accretion disks glowing with the heat of billions of suns. There are jets shooting out at relativistic speeds, powered by frame dragging and magnetic fields. There are space-times twisted into configurations that would have seemed like pure fantasy just a century ago. And you understand this? You know this. You're part of the universe's process of understanding itself. Now, let me bring this home with one final perspective. The question, why do some black holes spin near the speed of light, can be answered at multiple levels. At the most basic level, because angular momentum is conserved, and when matter collapses or accretes, the angular momentum has to go somewhere. At a deeper level, because the laws of physics, specifically general relativity and the symmetries that give rise to conservation laws, permit and even encourage extremes when the right conditions are met. At a cosmic level, because the universe contains environments, binary systems, galactic centers, merging black holes, where those conditions are met, where accretion is organized, where magnetic fields are coherent, where spin-up dominates over spin-down. At a philosophical level, because the universe is fundamentally a place where extremes occur, where the possible becomes actual, where the laws of nature are pushed to their limits. And at a human level, because we're curious enough to ask the question, smart enough to find the answer, and equipped with tools, telescopes, gravitational wave detectors, supercomputers powerful enough to test our theories against reality. All of these answers are correct. All of these levels are important. The beauty of science is that it works at all these levels simultaneously, from the most concrete and specific to the most abstract and philosophical. And that's what I hope you take away from this. Not just facts about black holes and spin parameters and accretion disks, but a deeper appreciation for how understanding works. How we build up knowledge piece by piece, observation by observation, equation by equation. How every answer leads to new questions. How the universe is comprehensible but inexhaustibly fascinating. Black holes spinning near the speed of light are real objects out there in the universe right now. But they're also symbols of the extremes nature can produce. Symbols of the power of human understanding. Symbols of the deep mathematical structure underlying reality. They're objects we'll never visit, never touch, never directly experience. But we can understand them. We can measure them. We can theorize about them and test those theories. We can incorporate them into our picture of how the universe works. And in doing so, we expand what it means to be human. We expand our circle of comprehension. We push back the boundaries of the unknown. So here's my final message. Stay curious. Keep asking questions. Keep learning. The universe is full of wonders, spinning black holes, gravitational waves, quantum entanglement, the accelerating expansion of space, the emergence of life and consciousness. And we're privileged to live in an age where we can understand so much of it. Why do some black holes spin near the speed of light? Because the universe is capable of producing such extremes. Because the laws of physics allow it. Because angular momentum is conserved. Because matter accretes and merges and collapses in specific ways. Because magnetic fields organize flows. Because we live in a dynamic, evolving cosmos where extreme conditions arise naturally. But also because we asked the question. Because we cared enough to look. Because we built the tools and developed the theories to find out. Because understanding matters to us. And that, ultimately, might be the most profound answer of all. Thank you for taking this journey with me. Thank you for engaging with these ideas, for pushing your understanding, for for spending nearly 4 hours exploring one of the most extreme phenomena in the universe. If you've made it this far, you're truly dedicated to learning, and that's something to be proud of. If you enjoyed this deep dive, please like this video, subscribe to the channel, and share it with anyone who loves learning about the universe. Drop a comment telling me what blew your mind the most or what questions you still have. I read every comment, and your feedback helps me create better content. And remember, the universe is far stranger and more beautiful than we ever imagined. Keep looking up, keep wondering, keep learning. Because out there, right now, there are black holes spinning at unimaginable speeds, dragging space-time into impossible configurations, testing the limits of physical law. And you understand them.